this is still for discrete charges. So we have summation sign. In the case we have so many charges, so eventually we have a continuous distribution. Then we can change the integration sign to integration sign, summation sign to the integration sign. Okay? So now we have rho, charge density, multiplied by the electric potential, and then we perform the volume integration. But still, you have to divide by 2 because you're always double counting. Okay? So now let's take a look at one particular example. So somehow, in space, we have a uniformly charged sphere. So the charge density at any location is the same. So basically it's a constant, right? Now we want to find out the electric energy being stored in this charged sphere. That's weird, right? In the past, we talked about charges, but we don't really look into that type of problem as energy being stored. But now you understand, if you want to have lots of charges in space, that is telling you it is acting like a capacitor, because in the process of assembling that charged sphere, you actually have to devote work. Okay? So with the presence of that charged sphere, it's a way of saying, hey, I have energy. Right? So try to appreciate the fact. I mean, everything we see is a form of energy. Okay? All right, so the first, we're going to look at the same problem using 2 different perspectives. First, I'm going to walk you through when we assemble this charged sphere with a radius of b, we are trying to assemble in a way as a layer by layer method. Okay? So we can deposit a thin layer of spherical shell with a differential thickness of dr onto the previous sphere. So eventually it grows up to reach the radius of b. Okay, so this is called the layer by layer assembly method. Right? In another sense, I can view the problem as, well, initially I have this smaller sphere with a radius of r, and now I add another thin shell of charges and cover it, right? So that now r is plus dr. So the sphere is getting bigger, right? So I can analyze the amount of energy required to assemble each shell onto the sphere. So if I integrate all the way the radius from 0 to b, I know the total amount of energy being stored or required to assemble this sphere. Right? So for each layer, for each differential layer represented by this checkerboard blue shell, each differential layer needs this amount of energy. The charge contained in that thin shell multiplied by the potential it needs to overcome. Okay? But that's easy because to properly describe this, the volume of this shell is 4 pi r squared, the surface, and multiplied by dr, and therefore you have the volume for that thin shell and multiplied by rho, because now we're fortunate. The charge density is uniform. Okay? So we have the proper expression for dQr, the total amount of charge enclosed by that thin shell. But EVR is simple, right? We already know that because we are trying to work against the potential of this green charged sphere. So this is actually Gauss's law, right? QR. QR means the charge, the total charge contained in this green sphere. So you only have to know its volume. Well, the volume is 3/3 pi r cubed rho. Okay. So therefore, for each thin shell, we need to devote this amount of work. Okay? And now we only have to perform integration from 0 to b. And that's it. Simple and straightforward. So the answer is quite complicated. 4 pi rho squared b to the 5th power divided by 15 and epsilon 0. Okay. So this is working in a layer by layer assembling approach. But the same problem can also be, the results can be derived by using this generic expression. Because in the end, we want to use this developed expression, right? The total energy is 1 divided by 2 integration of rho times the potential, and we perform the value integration. How can we use this formula? Well, the layer by layer approach is straightforward in making physical sense. Right? But this equation is also simple and elegant, but to use it, you have to be very careful. What do I mean? Well, eventually, because we're treating a sphere, so in spherical coordinate system, we have very good symmetry, right? And therefore, the volume integration can be reduced to, I have a surface, right? And I have the differential length. So this is reduced to a one-dimensional integration, right? Because in every direction, I have symmetry. So the volume integration is reduced to a line integration in the radial direction. So mathematically, it's not difficult. But usually for students, you will mess up because how to properly account VR. Look at the equation again. Rho, in this case, rho is not spatially dependent. It's a constant everywhere, so I can take it out. Outside of integration, which is nice, you have less chance of getting wrong. So eventually, you're trying to perform a line integration with the radius, and VR is the potential as a function of radius. This should not be very difficult. But I can assure you, if this is appearing as your quiz problem now, probably 90% of you will get it wrong. So think about it. If we only have one single charge, we know that V is Q divided by 4 pi epsilon 0 r. Right? Simple, straightforward. We went over it many times. But now the fact is, I have a sphere of charges. Meaning, this charge distribution is having a finite size, right? And therefore, when I deal with V of R in this case, it's different as compared to the single charge potential. Because here, you don't really care about the size of the charge. But here, you have to concern about the size. The size is big. For a single point, you don't care about its size. Okay? So therefore, this V of R needs to be analyzed carefully. You have to divide it into two particular regions. One is when you are outside, right? So when you are outside of this charged sphere, no matter where you are, the total amount of charge remains constant. Okay? So when you're outside, Q total is a constant. But what happens when you are inside? When you're inside? When you are standing a distance of R to the origin, when you are inside, the charge of this yellow sphere is actually radius dependent, right? So you have to take this consideration into account. Of course, we know that voltage potential is just the negative line integration of E field. And in this case, we're lucky. E field is only in the radial direction, so we perform a line integration in the radial direction. But now we have two parts, right? This is essentially saying when we use Gauss's law to find the E field intensity when you are outside, the total amount of charge enclosed is a constant. It is not a parameter of the distance, right? When you're outside, the total amount of charge is the volume of the sphere and multiplied by rho. It does not change as a function of distance. But when you are inside, when your radius is smaller than b and greater than 0, you have to be careful. In this case, you are evaluating only the charge contained in this yellow sphere. So it is the volume, but now the volume is distance dependent and multiplied by rho. Okay? So you have to separate into these two different regions. Outside and inside. Alright? And therefore, in your electric potential, you have to have two different regions as well. Right? Now, well, you can do this integration, I suppose. I have trust in you. You are all good students. Well, it's very messy, but in the end, the result is the same. As compared to the previous viewpoint, we assemble this sphere layer by layer. It has to be the same, right? The two results has to be the same. But what I'm trying to convey is, while using this equation, right, you have a continuous distribution. You don't care about where the charge is coming from, and you don't care about the sequence, which one's coming first, which one's the next. It's fine. You can use this equation. And you have to remember 1 divided by 2. You double count, so that's one fact. And the second fact is, usually you have to ask yourselves, you're trying to find out the potential as a function of space. And you get that result by finding the E field. But the E field, you like to invoke Gauss's law. But to properly invoke Gauss's law, you have to have a very clear mind. Do you need to break the problem into different regions? And therefore, you can have a proper formulation of the amount of charge being enclosed. Right? So let me repeat. For this simple case, when you're outside, no matter how far away, no matter how big your Gaussian surface is, once you're outside, the total amount of charge enclosed by this Gaussian surface is a constant. But when you walk inside of the sphere, right, then this is distance, and you form this Gaussian sphere, the amount of charge enclosed by this Gaussian sphere is now spatially dependent. Okay? So you have to divide the analysis into two different regions. Right? But, I mean, you get the same result. Alright, we have covered that charges are capable of storing electric energy. What about fields? I mean, field lines are invisible, or charges are visible if your eyes are good enough. And charges produce field lines. So is it possible that even the invisible field lines also contain energy? Well, we start with this same equation, right? But when we look at it, this is saying, I mean, mathematically, this is saying, if you want to have electric energy, you have to have charge distribution, right? Right? If rho is 0, that means between you and me, we don't have charges. Does that mean we don't have energy? Having 0 charge means 0 energy. Well, it seems like that. But now you have learned. I mean, we talked about the flux density, D, a new vector field. How is D formulated? Do you still remember this one? Divergence of D equals to the free charge density, right? So we are free. Now that we know whenever we have free charge, we produce flux density. So we can write down this rho as divergence of B, while V remains unchanged. Okay? So this is moving forward, telling you, well, maybe we don't need the existence of charge really being there, but in some space, the field lines the charge generates also is a form of energy, right? So we don't know, we don't have the adequate mathematical skill to perform the integration of a vector field performed after divergence and multiplied by a scalar field. We don't. So this is the point where we would like to introduce a vector identity. What we have is the black one, right? We have a scalar potential multiplied by the divergence of a vector field, and that is equal to the divergence of the scalar field multiplied by the vector field and minus, I move this one to the left, and minus the vector field, making a dot product with the gradient of the scalar field. Okay? So this is a well-known vector identity, which means electric energy, initially we have this black term, and we perform the value integration. But now we can change it, and it equals to these two value integrations. Right? This is through vector identity. They must be equal. I still don't know how to solve it, but I want to change the expression to something I like. Remember, I'm trying to find the electrostatic energy stored in fields. So somehow I'm looking at a way to change the potential charges to field quantities. Field quantities means D and E, right? So take a good look. I mean, which one can I change to field quantity? Gradient of V, right? If you still remember, negative grad V is E field intensity, right? So I replaced negative grad V to E. So when you look at this new expression, well, this is something I like. So this brown portion is telling me, oh, even at its spatial regions where I only have field lines, it is also having some kind of energy. Right? E and D, these are really just having fields. So in a spatial region without having a particular charge, you can still calculate its energy. Okay. What about the first one? The first contribution, well, the potential multiplied by the vector field flux density, but now is having a closed surface integration. Initially, in our value integration, this value integration goes to infinity, right? So now this closed surface integration is performing an integration over a sphere with infinite radius. So let me try to convince you. The first term goes to 0. Why? If you have a very big sphere, we know the surface is 4 pi r squared. So the surface is having an r squared dependence, right? But to our knowledge, electric potential is 1 over r dependent, while this d is 1 over r squared dependence. So you multiply the two, you have 1 over r squared multiplied by 1 over r. You actually have inverse r cubed. And you multiply by the surface, 4 pi r squared, you still have 1 over r. But when r is approaching infinity, this first contribution goes to 0. Right? So this is telling you, if we have the proper expression for the field, we can also calculate the resulting electric energy in that part of space. Okay? So let's try to use it. We look at this parallel plate capacitor again, and we ask ourselves, what is the resulting energy stored? I mean, we can also calculate it from the field it generates. Right? So when these two plates are very big, the area size is very big as compared to the distance, we have uniform field. And that field is V divided by D. V is the potential you apply. The potential supported by the battery. Okay? So we know the expression of E, just put it there. Right? So the energy contained in this simple capacitor system is this. But the integration 0 to D to Y is simple. It's just multiplied by D. So basically, in this capacitor, the total energy stored is 1 over 2. You know where 1 over 2 is coming from, right? 1 over 2. And this amount. But if you still remember, epsilon times S, the surface area, divided by the distance between the two plates, is just the capacitance, isn't it? This is actually something you were forced to memorize as a high school student. The energy stored in the capacitor is 1 over 2 CV squared. Right? But now you know where it's coming from. So we can extend it. So in the future, if we can calculate the energy stored in some device or space, then we know that the energy is equal to 1 over 2 CV squared, so we can deduce the corresponding capacitance value. Right? So this is a very simple example, but really to convince you, well, eventually, for whatever system, whatever material you use, whatever geometry you use, the stored energy can be formulated with a process of, and can be related to capacitance, right? So in the future, you have this energy multiplied by 2, divided by V squared, and you have the capacitance. Okay? So with that, I formally close the session for static electric field. So we introduced the E field intensity, E, the vector field, and then we talked about materials. We introduced D, the flux density, and then we talked about capacitors. Right? So hopefully with that information, you have a clear understanding to electrostatic fields. Right? Thank you. So next week, we're marching into steady state current. It's a new chapter. Right? I'll see you next Monday.